Okay, so actually we are not going to do Riemanns today. I'm much slower than in the videos. But we are going to prove the theorem that I promised you. And it's most of Riemann, so that's fine. We meet for today. Anyhow, I don't have a choice. So now we are ready to prove what I promised you. So for any function, proper function in a function field, the degree of the zero divisor is the same as the degree of the pole divisor, which tells you that every function has the same number of poles and zeros counted properly. And that number is not just some number, it's this number. Fantastic. So let's do the proof. It will take like the 15 minutes that we have, and it's really weird. Really, really weird. One of the weirdest that I saw. Yeah, it's this one, right? Yeah. Okay. So it's enough to do the infinity case because that's the same with inverses. So if I prove this equality, then that will immediately be happen because I can take x inverse, and the x inverse of the zero pole of the x inverse is the pole of x, and k of x is the same as kx inverse. So we'll just do suffices to do infinity. And actually, we know something. It's funny that we can use it. So we know that this is at most that. We prove that. So we're only going to prove. How can you use that? Like going to prove that the lower bound holds. Which already hints that something weird is happening, because how can you just do like this one? That's really weird. The other one makes sense somehow, but this is weird. I mean, the other one wasn't easy. But once one understood the degree has a relation to the residue field, and we shifted things and so forth, it was more apparent what you should do. So let's call this number n, because it will appear a lot, the degree extension. And we are going to do something weird, okay? I can't explain it, just I'm going to follow it. It's a really washed out proof. People walked on it for all the time, so that's like the succinctest way of doing it, and it feels like that. So what we are going to do is we are going to take y1 up to yn in f that are linearly independent over k of x. Right, you can do that. You just take a basis or something. You can do that because that was n, the degree extension. And we may assume these yi's are integral. Right? This is the g thing. You can multiply by g. Integral over k of x. Okay, multiply by g. Now, the previous claim 8, by claim 8, we know, that's actually, so let me do it differently. I'm going to use claim 8, but I think it's written weirdly here. So what I'm going to say is that when I explain it using claim 8, so we know, so what I'm saying is that, and let me justify that, we can choose an integer k, large enough, I mean, such that, I'm going to explain why we can do that, but for every j. Right, so you started with this x. The x was the given in the theorem. And then I took a basis that kind of encodes n, right? I need n. So this is y1 up to yn. And what I want to do now is I want this divisor to be larger than some divisor. So I want to choose k large enough so that this will hold. But why can't I? So let's see. So the point is that by the previous claim, we know, it's actually a bit tricky. We know that VP of x larger or equal to 0 implies that VP of yj because of the integrality. Right, this is the claim from before. We know from the before claim that if x is defined at a point, for any point, then any integral element over it is defined at the point. So we know that. So this means that if something is positive, here, which means it's a pole of yj, then it's also positive here. Right? So I mean the contrapositive of that, maybe I should do the contrapositive. The contrapositive of that tells you that Vp of yj is smaller than 0 implies Vp of x is smaller than 0. Right? These two are equivalent. Right? Saying that. I just do the contrapositive. So an element appear here if Vp of yj is smaller than 0. That's the pole divisor. But with the minuses, right? So if Vp of yj is like -5, it appears here as a 5. Right? And what I'm claiming is if 5 appears here, then a non-negative number appears here. And that's why we're done. Because for every positive number here, there is at least one here. So you can take k large enough to win that number. And there are only finitely many n's. And we proved that the support of this is finite. So there are only finitely many numbers that we need to win. And we can always win them because of that. The problem was if it was a 1 here and 0 here, or worse. There is no worse. I want to say 1 here and -1 here, but that doesn't happen. That's a positive divisor. Everything is non-negative. So the problem would have been if there was something in the support here which is not here. But it doesn't happen because of that. If there is something if there is a 1 or 2 here, it will be at least 1 here. And so you can choose k large enough for which this. Yeah. Good. So that's why we wanted the integrality. That's all I needed from it for today. Good. Because for that to happen. I choose them to be integral. No, if they are not integral by the previous claim, we can make them integral by multiplying by g. Right. Oh, wait, yeah. And I should say they still remain independent over k of x. Maybe I should say that. Right. So I multiply by g of x, they still have dimension n. Yeah, that's good. Yeah. Right. I change them, and so now comes a weird part. Now take any L and any I, okay? And I'm going to do the following. I'm going to consider, through me, I'm going to consider this thing. For no good reason initially. So if you open this up, so this is I times x, the principal divisor of x, plus the principal divisor of yj, plus k times the pole divisor of x, plus L times the pole divisor x, which you can also write as you open up this to its pole and 0 divisor. Just go with me. Right, so I just opened the principal divisors to the pole and 0 divisors. And now I'm going to just rearrange things so that you can see something. So they're all equalities. So just trust me that if you open this, you get that. It's just a matter of doing this. And now the point here is that this is non-negative because we chose k large enough so that this would be non-negative. And this is non-negative. This is non-negative because I is smaller than L. So this is non-negative. Everything here is non-negative. Like these are non-negatives, I is non-negative, everything is negative. So this is non-negative as a divisor. Why do I care? Because this means, if you look at the beginning, this means that these functions all of these functions belong to the Riemann-Roch space, to this Riemann-Roch space. Right, for any L and for any I between 0 and L, this is non-negative. So this means that all of these functions belong to this Riemann-Roch space. That's the definition. And so its dimension is at least, n times L plus 1. Right, you have n functions, the y's, and L plus 1, the i's, and L is a parameter. Right? They're linearly independent, right? Sorry, and they're linearly independent. This was the first item. Yeah, good. These are linearly independent of K, because the yj's are linearly independent of K's. And we saw, actually I gave you as an exercise, that dim A for A non-negative, if you remember, we had this little problem exercise. So this means that K plus L times the degree of x infinity, which is just the degree of K plus L times the x infinity, is at least n times L plus 1 minus 1. I just plug in A to be this K plus L times x infinity. And noting that the degree of K plus L times the divisor is just K plus L goes outside. And that's cool because now, so I can write it like that. I told you it's weird. My weird threshold is very high, so I really mean it when I say it's weird. So I just divided by K plus L, okay? And remember, K and L are now not real, they're just like parameters that we had. I choose K large enough, and then L could have been anything. And this number, you see, it approaches, maybe from below, but it approaches n as L goes to infinity. So n is something that was given, K is something that you needed for this to happen, really. And then L was completely free to do what he wants. And you prove that a lower bound on the degree of this divisor, which is something that, as L goes to infinity, this goes to 1. I don't mind K, because as L goes to infinity, it goes to 1. So it's, it goes to 1, and you have a little bit of slackness here, but at some point it's going, you can actually compute it, at some point it's going to pass n minus 1. And it's an integer, so it's n. Very weird. Yeah, okay. So next time like in 20 minutes, we're going to define the genus and prove Riemann's theorem. That was the main part of it. Yeah, but we should stop here. I think it's a good point. Okay, see you next time.